You guys can't see this, but it says no displays found on wireless. Yeah. Okay. Oh, there we go. For 704. Look at that. It's almost like there's a whiteboard in the room now. If you're the group that normally sits at that table, you should sit somewhere else today. But I guess you guys figured that out, right? Perfect. Only 5 minutes late. That's not too bad. Okay. So today on the syllabus, it used to say something about manufacturing metrology or something. Anybody know that? Did anybody know that's what it said about today on the syllabus? Yeah. We've talked about that like twice already. So I fixed it. Today I want to talk about CNC motion and CNC setup and crashes in machine tools, and how to try to avoid crashes in machine tools instead of watching them. Who in the class has ever hit the emergency stop button on the machine tool? Well, that's a lot of you. Why did you hit it?
Well, sometimes they told us if they did, like, when we finished running the program.
All right, so you used it to sort of end the operation of the machine.
Yeah, to make sure that
You were finished running the machine, and you hit the e-stop button before you walk away from the machine, so that if somebody else wanders into the machine shop and inadvertently presses a button, it doesn't start an automatic operation. That's the reason we tell people to use the emergency stop once they're done with what they plan to do. So put your hands back up if you've pressed it for a different reason. Over there in the back. Oh, that's right. You were the infamous wrong parallels for the lab setup and broken window and all that stuff, right? Did the window break on your part? Oh, the window broke on your part. Did you hit the e-stop? You panicked and Kelly hit it. So actually, I years ago, was diagnosed with a repetitive stress injury in this shoulder. And so it's one of these, you go for your annual physical and you're talking to the doctor. The doctor's like, is there anything else you want to talk about? I'm thinking, oh, you know what? My shoulder always hurts, like right here. And so he, pushes it around and manipulates it and all that stuff. The stuff doctors do to your shoulder when you say it hurts. And he says, I think it's this repetitive stress injury, and it's like tennis elbow. And he says it comes from this motion. And so I'm thinking, all right, I'm not a Nazi that I know of, but I do make this motion all the time, usually diving between students to hit the E-stop on the machine tool. And it was at that moment that I realized machine tools were way cheaper than shoulders. And I stopped diving between students to hit the E-stop. And then it was just like, you should stop that. E-stop. And often you'll hear the other students in the classroom when something goes bad. You hear a lot of people scream, E-stop! Who's heard that? Did somebody say that just before Kelly hit it? She just did it. Nobody.
Have you ever seen someone get their tie stuck in the machine?
I have not physically been there when somebody got their tie stuck in the machine, but it has happened. It is a good way to die. So don't do that.
It was like image. It was actually
Yeah, I made the image actually, or I'm the person responsible for the fact that that image is up there. It's kind of weird that the screen projection is so sucky, but maybe it just needed something new to focus on. Okay, so all right, so who else has done an e-stop for cause? Tell me the story.
So yesterday, after fixing the burner part on the lathe, I asked the TA, okay, so now we home the part and run it, right? He goes, nope, just run it. So we hit run, and the tools turn, smacking the tools.
The answer was we home the part,
Yes.
we press reset, and then we run it.
Yes.
So this reminds me of, I think, my most spectacular crash ever. So if somebody tells you that they're a CNC operator, CNC machinist, and if they tell you that they've never crashed the machine tool, you know one thing for sure. They lie about other stuff too. In my most spectacular, I started about 6 a.m. I was setting up a job that had to be delivered on Monday. So this was at my machine shop. And that's why I was working, because it was the weekend. And so I'm setting up a job, has to be delivered on Monday. And I've just done 4 hours of setup. You get the fixture in just the right place. It was a really fancy fixture, really fancy tool. The tool is about $2,500 for the tool itself. One tool for the operation, but you got to get the setup just right. And I said to my my business partner at the time, I said, I'm ready to go. And he said, don't you want to run that in dry run? I said, no, it'll be okay. Cycle start, step away. This is my favorite thing to do in the machine shop. Press the green cycle start button, turn around and walk away. Because once the machine tool is working, you can go do something else, right? That's the joy of the automation of the CNC machine tool. And it did not make the right noise. So as quickly as I could, so I recognized the wrong noise as I was turning away from the machine. Quickly as I could, I slammed my hand onto the E-stop. So $2,500 tool, gone. Fixture out the side of the mill, laying on the ground outside. Because, so send it home, press reset, then press cycle start. So my mistake, and as soon as I heard the noise, I knew exactly what my mistake was. It wasn't that I hadn't set it up right. It wasn't that it was the wrong program. It's that I ran a simulation of the program. Right? We always have you simulate before you make the part. And the purpose of simulating before you make the part is, well, it's a couple purposes. One, it will catch some errors that you miss in the simulation in the CAM software. So if you forget to put in a speed or a feed or something like that, or if you put in a speed or a feed that the machine's not capable of, that'll throw an alarm. If you fixture the part too far to one side of the table or the other side, it will say we could run the program, but we can't reach that spot. So it'll throw alarm. And of course, if the picture of the simulation doesn't look like what you were expecting the program to look like, it's not the right program and you need to fix that part, right? So that's the sort of the three reasons we simulate on the controller. Anyway, so I had been simulating on the controller like we tell everybody to do. But it was a long program. And I'd simulated it before. And I'd run the program before and doing setup steps and trying to make sure that all the tools were in the right places and all that. And so I finally was done. I knew that I could make a good part. I knew that the next part that came off the machine was going to be a production part, not a setup part. I'd made several setup parts already. Next one was a production part. Cycle start, turn around. Spindle's not supposed to spin first. Tool change is supposed to happen first. So as soon as the instant I heard the spindle spin up, I knew something was wrong because I was expecting a tool change when I pressed the button because I knew which tool was in the spindle and it had to use the other tool first. Except when you restart the program in the middle, which would happen if you watch part of the simulation and then you pause the simulation and then you go to current commands mode and you say, all right, now I'm going to run the part. It'll start right on that line of code that you had selected, which is the one that it was on when you hit feed hold in the simulation. And so, yeah, cost. Well, the first 4 hours was gone. The next 4 hours was gone, plus an extra hour because the tool, it was the grinding wheel, and you have to true the grinding wheel. And so there's a whole process for that. But hey, you know what? Still had to deliver those parts on Monday morning. So yeah, go home first. And the reason we tell everybody to go home is in case you've made that stupid mistake that I made. So a lot of the rules that we have in our lab for safe operation, and I'm more meaning safe operation as in don't break the machine tool. A lot of those rules have been established because of past mistakes. And so that send the machine home and press reset, those exist because of my past mistakes. And that's probably the most glorious of them. But so we have this 6-step checklist that we have people fill out when they run the machines. You guys have all seen the checklist, right? So what are the steps on it? This will be important for your lab practical exam, by the way. So simulating the CAM software. So simulating the CAM software tells you, the operator, what you think, or what the computer thinks the program's going to do. All right, so simulating the CAM software. There is some flexibility in the order that you do the steps, but you have to do all the steps. So you have to set the work offsets, and that's part of what we're going to talk about in today's class is what happens physically when you set the work offsets. But the overall is setting the work offsets tells the machine tool where the work piece is relative to where the 0 is that you set when you created the program. So we set the work offsets. What else? Yes. We do check the distance to go, and hold that thought because I'm going to do that one last. Okay. We set the tool offsets. And you can set the tool offsets or the work offsets. It doesn't matter which order typically. Depending on the method you use to set the tool and the work offsets, sometimes you use one of the tools to set the work offset, in which case you have to have set the tool offsets first. But if you're using the probing system like we normally use in the machines, it doesn't matter which order you do them. as long as you don't calibrate the probe in between the two instances. Right? As long as it has the same calibration, it'll measure those relative distances. So we simulate the cam, set the tool offsets and the work offsets. We used to have a 5-step checklist because I combined the tool and work offsets until we determined that that was not, yeah, we shouldn't combine those because you could do one, forget to do the other one, and you wouldn't have a separate check mark to know whether you did the other one. You have to do both. Okay, so what's the next step? And you have to do this step after doing the set the tool and the work offsets. You're the star of the show today. Simulate on the controller. That's what I was thinking of. So simulate on the controller, and that's we talked about that. Can tell you, did I put the part too far over? Did I load the wrong program? Is it the right program? And then, are the feeds and speeds within the capability of the machine? Because it'll alarm out at that moment. And then after you press cycle start, right? We press cycle start, and that's a green button. And I always say, don't ever press the green button in order to find out what's going to happen. Right? I mean, you will find out what's going to happen when you press the green button. But when you press the green button, you should already believe that you know what's going to happen. And your belief of knowing what's going to happen is going to be from doing the simulation on the cam, doing the simulation on the controller. So when you press the button, like when I pressed the button, as soon as I heard the noise, as soon as the spindle started and I expected the tool changer to operate, I knew that it was wrong, right? And so you should have some expectation. I didn't know fast enough that I could stop it, but that's because of 100% rapid, because I'd made several setup parts. I knew it was going to work, probably. So as we do this check distance to go. And so one of the labs, we're going to start the second half of this week. And so if you've already done the burner bottom part, the big brass part in the mill, then you'll get a chance to do this week. Otherwise, you'll do it next week. But it's a lab exercise that we've developed to allow you, before doing your lab practical exam, to practice checking the distance to go. So we have a series of programs that we've created. And we've already set the offsets for you for those programs. So you don't have to worry about doing the setup step. Some of them will crash the tool into the workpiece. Some of them will operate correctly. And we developed this lab so that you had to, at the moment of check distance to go, when you do that check distance to go step, you look at the line of code that's highlighted, it'll say something like Z 0.1. Well, that means that it's going to the Z value 0.1 positive, because it said Z 0.1 positive. So it's a positive value above the Z value where the work offset was set. So if you set the work offset on the top of the stock material and it says Z 0.1, that's where the tool's trying to get to at the moment of pressing feed hold. When you press that feed hold, you look at that line, it says where it's going to. And then you look in the machine and you visually estimate how far away it is. So when it's this far away, it's hard to do the visual estimate. But you could press the stop button, stop the spindle, and you could reach in and get a tape measure and measure it. You could do that. I usually wait till I can eyeball it to be about an inch away. I feel like I can eyeball that inch distance. And this is why we reduce the rapid speed. Right? We set that rapid speed to, on the mini mills, I'll use like 25%. I think I asked in class yesterday who had done a tool change at 5%. And that is super slow, right? So we don't want to do that. You can change that rapid speed at any time during the program. As it's moving, you could, all right, it's doing a tool change, let's go to 50%. finish the tool plane, just go back to 5% because we're worried about the coming down part, right? If you're worried about it. With the mini mill, I typically run it at 100% rapid because I've run it so many times that I've got the timing of when to press the feed hold button. If I'm nervous about it, what I'll do is I'll let it finish the tool change. After it finishes the tool change, I'll hit the 25% rapid button. And then it's coming down, and I might hit feed hold at this moment, hit the 5% button if I'm really nervous, because I know that it's a close clearance, that it might hit even if everything's all set up correctly. Right? But as that tool's coming down, normal operation will be doing 25% rapid. The tool's coming down, press feed hold when it's about an inch away. You look inside, you say, oh, that's about an inch. On the controller, you can get to the distance to go menu. And depending on which machine you are, it's a slightly different process to get there. But you get to that distance to go menu, and it'll say Z negative 0.981. So if I look in, and it's about an inch away from the part, but I know it's going to 0.1 above the inch. So that would be like 0.99 then, right? So 981, and I'm estimating that 1 inch. Yeah, I'll buy that. Probably set it up correctly. Press cycle start, let it happen. If it says negative 0.6215, and it looks like it's an inch away from the part, and it's still doing rapid Z down, yeah, it's probably going to crash, right? So that's when we, at this moment, because of feed hold and reset is enough, but because of the frustration of that moment of realizing I screwed up the offsets, because that's the moment we realize you screwed up the offsets. I usually hit the E-stop just out of frustration, but it doesn't have to be in earnest, right? You don't have to cause a shoulder injury. The doctor said that one instance of that motion is enough to cause the injury. Funny aside, because of that repetitive stress injury in this shoulder, when I was having a heart attack that exhibited with right arm pain, I did not go to the hospital because I thought it was my shoulder acting up. So avoid the shoulder injury because it could kill you. 4 days took me to go to the hospital. All right, so that's the operator checklist, right? Each tool as it's coming. After you've done it once, after you've run the part and it didn't crash, and now you're going to production mode of running that part, especially if you've got a part stop, so you're just putting every part in at the same location. Like we did the Y block, we had part stops, right? You didn't have to set the X and Y offsets. We had those part stops. You're just putting the next part in. It's going to cut exactly the same way. You can go to that 100% rapid, press cycle start, walk away. It's my favorite thing to do because the CNC machine is supposed to operate automatically. When we first got those machines, I was still a graduate student here when the first Haas CNC machine tool came. And we were pretty excited because who was born before 2001? Yeah, I guess I should raise my hand too, right? Yeah, so all the rest of you, the machines you've been using for lab are older than you are because they were all made in 2001. And so when I was a graduate student, we were in the case of all of the machine tools were older than all of the students and most of the staff. And so when we got into these brand new machine tools in 2001, that was pretty cool. And so we were all pretty psyched about it. So one day can't remember what the part was. We're making some part. And we thought it was really cool. It was probably like 4 holes in a steel plate or something. It was not a very fancy part, but we thought it was cool because the machine was doing it all. So we're all crowding around, watching the machine go, because the first part's kind of fun to watch, right? So the department head, the program director came in. What are you guys doing? We're machining this part. Like all 5 of us machining this part, right? What are you guys doing? We're machining this part. He looked at us, he looked at the machine, he looked at us. What's the machine doing? Because the machine was machining the part, right? We were just standing there watching it. All right, anyway, so that's our safety checklist. I figure, so I mentioned that we add different steps to the checklist and our procedures based on our experiences. I figure it cost about $90,000 in broken machine tools to develop that safety checklist. And since we've started using it, I cannot think of a single crash that cost money that couldn't be attributed to somebody skipping a step on the checklist. So do the steps on the checklist. All right, so today's about machine tool motion, setup, and crashes in CNC machine tools. The checklist is about avoiding those crashes. If you've done those steps, you may not make the part you wanted, but the part you make will probably not break the machine tool. Okay, and that's in lab practical exam. We have a very simple part. We ask you to simulate in the CAM software, set the tool offsets, I think it's 2 tools, might be 1 tool. It's 2 tools. Set the tool offsets, set the work offset, reduce the rapid speed, run the program, and check the distance to go for the 2 tools. If you do all of those steps and do not crash the machine tool, then you get 100% on the lab practical exam. If you can't remember how to do one of the steps, but you remember you need to do it, and since I'm pretty sure we're going to tell you to open the checklist before you start, forgetting that you need to do it is pretty much on you. If you don't know how to do one of the steps, but remember you need to, you can ask the PLA that you're with, how do I set the tool offsets? And they'll tell you how to do it and deduct 5% from your grade. If you skip one of the steps and move on to the next step, whether you crash the machine or not, it's 25 points off. Because it crashed the machine or could have crashed the machine. So, but if you don't know, if you recognize the fact that you don't know how to do it and you ask for help, it's 5% off. So there's what, 6 things? So if you ask how to do all 6 things, if you've never walked into the lab before and you ask the PLA to show you how to do each of the steps, you could still get a 70% on the lab practical exam. Because my goal is that you recognize when you get to the edge of your knowledge and you ask for help. If you're willing to get to the edge of your knowledge and ask for help, then I believe you can safely operate the machine tool, even if you don't know how to operate it, as long as you recognize that you don't know, right? Is that fair? Oh, and if you don't get above an 85%, I think we make you take it again. It's kind of like the driver's test. Who failed the first time they did their driving test? No, the driving part.
Oh, I actually passed it.
Anybody else? I failed the first time through. Anybody else fail the first time through? You did? You did? Are you embarrassed to say why? Parallel park. You drove too slow and he thought it was a hazard. I think you could sue for discrimination on that one. I ran a red light. Just saying. If you're gonna fail, go big. In my defense, there was a delivery van blocking the no turn on red sign. And I wasn't from the town where I was taking the test, so I don't know the intersection. And I asked the cop that was sitting next to me, are we allowed to make a right turn on red at this intersection? Because you can't see the sign from where I was sitting. And he said, I'm not the driver. So I looked around and I said, well, I don't see a sign, so I'll go ahead and make this right turn on red. Yeah. Now there's a delivery van blocking the sign, like illegally parked, blocking the sign. Oh, well. Everybody's got to make a mistake once. And if that is the extent of your driving mistakes, accidentally once making a right turn on red safely without killing anybody, that's a pretty good day. All right. All right, so CNC motion. How does CNC machine tools move? Yes.
Sorry, before you go to the next one, you only listed 5 out of the 6 steps.
Oh, reduce the rapid speed. And reduce the rapid speed to the speed that you're comfortable with on that particular machine tool. And you got to do that before the check distance to go, otherwise it's kind of useless. And so we talked about it, but we didn't call it out as a step. And so the reason I say to the speed that you're comfortable with on that machine tool, the mini mills, full speed rapid is 600 inches a minute. And so if you have a 4-inch long tool in the spindle, from the tool change height to crashing into the table, just assume there's no vise there at all, is less than a second at full speed rapid. Just because the mini mill is kind of short, so it doesn't have very far to go. But you do that to 25% rapid, now you get a couple seconds. A couple seconds is plenty of time to react when you see something moving, if you're paying attention. We have another machine, the Mill Drill Center, which is the big boxing machine that's sort of right in front of you as you walk into Washburn 108, so the room with the robots and stuff in it. Full speed rapid on that machine is 2,000 inches a minute. So 25% on that machine is like 100% on the mini mill. So that's why I say pick the speed you're comfortable with. The VM2 moves at roughly the same rate as the mini mill. I think the super mini mill moves a little bit faster. All right, so yes. Depends. Which wrap? I have never timed it. You can see it move. But I recommend bolting the vise down to the table before operating it. And that's totally different story also my crash, though. And I would say that's not my fault, but it was definitely my fault too. Oh, when a machine crashes, whose fault is it? Whoever pressed the go button. Regardless of what somebody else told you about what they did, regardless of if it was the program I created and gave to you and told you this program is bulletproof, just run it. If you're the one that pressed the go button, it's your fault it crashed. It's like those wastes. Some of those wastes we can get rid of. Some of them we can't get rid of. But your fault. What's the punishment for crashing a machine while you're a WPI student?
I was going to say, like, if you're the one it's your fault. Similarly to how, like, if you're
I suppose not your fault. You're responsible.
Yeah.
So know what you're doing and know what you expect so that you have some basis to hit that e-stop.
It's similar to, like, being involved in a rear-end accident, but if you're in the car behind and you're the one in the rear end car in front of you, it's your fault.
Yeah. So, yeah, I mentioned that my wife was in a car accident a couple weeks ago. And so we'll bring up that for responsibility and fault. This is more philosophical thoughts rather than machine tool thoughts. So somebody ran a stop sign at 40 miles an hour and T-boned her. She didn't have a stop sign. She was just driving along 25 miles an hour, right? Whose fault is it? Right. So we could agree that it's probably his fault that the accident happened. But what if she hadn't hesitated at the last light? What if when it turned yellow, if she had gone through it instead of stopping? She wouldn't have been there when he ran the stop sign, would she? So it may have been his fault, but we're all responsible for what happens to us. Anyway, that's life. And she's okay. Another doctor's visit yesterday, and they said no surgery. Probably. They're going to keep saying probably until they take the cast off and tell her not to put one back on. But all right, so machine tool motion. How do machine tools move? You've all seen them? How do they move? I say there's 3 ways a machine tool moves. Some people argue with me and say it's 4. So I'll get rid of the 4th way, the one that I don't count. The spindle spins. Spindle spins, that's motion. That's not one of the 3 ways I'm talking about. Yeah. So XYZ, so Cartesian coordinates. And we can certainly use Cartesian coordinates to describe the motion. We can certainly use Cartesian coordinates to describe the endpoints of the motion. Yes.
I think Cartesian coordinates will be
You could, but we use Cartesian anyway. I agree, you could. Excuse me. So the mechanism of motion and not the direction of motion is what I'm worried about here. And so the machine tool gets a command to move, and the code that we use to command it is called G code, M code, G and M code, NC code. Any of those words can work to describe it. It's contagious, I guess. Hope it's not COVID. All right, so the mechanism of motion. So we've all seen a machine tool. Who's a robotics engineer? You're a robotics engineer. Who else? A couple of robotics guys. So what's the mechanism that causes the motion? If you diagnose it as a robotics engineer. Well, no, we use Cartesian if we're going to describe it mathematically, but what's the physical mechanism? If you were building the CNC machine tool and you're building an electromechanical device to do these motions, what's the mechanism you'd use? Yeah, go ahead. All right, so we might have some linear rails, and so they're guides. And if you put the table on the linear rails and you pushed it back and forth, it'll go back and forth like this. It's kind of like putting the train car on the train tracks. If you push it back and forth, it'll follow the train tracks. He said linear, so presumably we make the train tracks be straight, right? So we got some physical rails that the table moves back and forth on. And you said driven with a ball screw? A ball screw attached to a stepper motor or a servo motor. All right, so we've got, so who's ever taken like a bolt and a nut and like spun the nut and watched it go down the bolt, or spun it and watched it go back up, right? We've all got this experience. So it's very similar to what's happening under the table in between the two rails. Is we've got a screw. Now it's not like a quarter 20 screw, right? It's got a fancy shape on the threads, and you can Google it and look it up about how the shape and what's so good about it. And then you said a ball screw. So the way the ball screw works is instead of just having like a nut on there, it's this fancy nut with ball bearings and fluid pressurizing the ball bearings, pushing on the thing so that it's always making contact with the screw threads. So that when I change the direction of rotation, it changes the direction of motion. And so if you've got any clearance in there, anytime you change the direction of motion of the rotation, there'd be a little gap. And then it would start moving backwards because you'd have backlash. And so that's what the term backlash means. It's how much you have to go rotationally before you start moving linearly. And so if you've got these really tight ball screws, the backlash is smaller and therefore harder to measure. I wouldn't say non-existent. But if you know exactly what it is, you can actually correct for it in software. Anyway, so we've got these rails, these linear guides, and we've got a ball screw, and any CNC machine that I've seen has a servo, not a stepper, but some motor that causes a control. And the servo motor, with a stepper motor, you send it a pulse and it moves a step. And you send it a pulse and it moves a step. You want it to move 5 steps, you send it 5 pulses. With the servo motor, you're actually doing feedback control. You're sending it the signal to move that direction, but you're also seeing, did it move that direction and how far did it move? Did it move to the right place? And so like a servo motor, if it goes, I got my marker here, we got the whole screen going on. If I wanted to, so what do we got? X and Y here. And if I was going, say, at 45 degrees to this point. So I was going to go to those 2 points. When I send it to go there, when it's moving in this Y direction, it might do this and then do this. right? So it may go a little bit past where I told it to go. It says, oh shit, I went too far. I got to back up. Oh shit, I went too far again. And so that's feedback control. And eventually it'll be at the right spot. The other thing, so the spindle is also a servo in these CNC machine tools. And so you can tell it to go 0 RPM. And it will use all of its ability to not rotate. And there's big warning stickers on the machines. Do not set 0 RPM to change the tool. Because you'd think it could hold against your wrenching on the tool, right? Yeah, except if it gets an error signal too big, what it decides to do is spin all the way around and then stop. And so you don't want it to spin all the way around with that wrench attached and hit you in the head. You had your hand up? You can get close, yeah. But the machine tools typically have these servo motors. All right, so that's the physical mechanism. So the X has one of those servo motors with the screw and the guides. The Y is bolted to it, and that's got one of those servo motors with the guides and the ball screw. The Z has one of those, and the spindle is bolted to the Z. So that's our typical mini mill, our 3-axis mill. X, Y, and then the spindle moves up and down in Z, right? Okay, so the commands we can give it to move, there's only really 3 motion commands we can give it. We can tell it, go from where you are, or as I like to say, wherever the hell you happen to be, to where I told you to go as fast as possible. So go from here to there as fast as possible. What do I have to know in order to program that? Yes. No. I don't have to know how fast possible is. If I want to program, go from here, go from wherever the hell you are to the point I told you to go to as fast as possible. What do I have to know? You say we need the current and the target positions. I say you're wrong. We just need the target. It's going to move from wherever the hell it is when it gets that line of code. The programmer never knows where it is when it gets that line of code if somebody inadvertently starts the program in the middle. It's going to go from where it is. Now, the way you know where it is as the programmer is it is at the last place you told it to go. Which is why often in these programs, the first command we give it is go home. Right? So if it's at the home position before we start doing all the rest of our stuff, at least we have some idea where it started. And the people doing the setup, the people doing the operation should know that it should be pretty close to the home position when you start it. Which is why we say go home and press reset before a cycle start, because then if it tool changes at the first thing, it won't rotate into the chuck. All right, so if I want to go, so here's where I think I am. So that's point A, we'll call that A. And here's point B. And that's where I want it to go. And the command, the G code command, you don't have to know these commands, but the ones that frequently get used, you'll remember. The G code command is G00. And so let's say this is a coordinate system, and we're starting at point A just to make it easier. And so we need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So B is 12. And 1, 2, 3, 4. So the coordinates for point B, Cartesian coordinates, is 12, 4. Right? And so the command to tell it to go from A, because we're assuming that's where it is. But remember, if somebody left it in an unsafe state like me, it might be over here. It might not be here. But let's give it this command. The G00 X12, right? X12 Y4. So we're assuming we're not moving in Z in this motion. We're just moving in XY. But if you wanted to move the spindle up or down, you could have a Z in the same thing. So that's the line of code. Use a decimal place. If you omit the decimal point, you don't have to put the 0 after it. But if you omit the decimal point, it assumes you mean the smallest increment that it knows. And so on the Haas machine, that's 1/10,000th of an inch. So it would move 12 tenths and 4 tenths instead of 12 inches and 4 inches, right? So that wouldn't be where we wanted it to end up. But that's that one line of code. And the motion that it would take would be this and then this with some slight overshoot there and some slight overshoot there. So the way it's going to do that, it's going to start the X servo motor as fast as it can spin and start the Y servo motor as fast as it can spin. I'm assuming they both have the same maximum speed. And I'm assuming they both have the same gear ratio. So it's going to spin them both the same as fast as they can go. And so it'll move in a diagonal line until it gets to the Y value that's correct. So as it gets to the Y value that's correct, it'll turn off the Y motor. It'll just move the X. So that's rapid. And so that's that 510 or 525, 50, 100% rapid. That's what we're controlling when it's a rapid motion. We program rapid motions when we're not expecting to cut the material. The other way a CNC machine tool can move from A to B is in a straight line. The command for that is G01. There's a pattern here. G00 is rapid, G01 is linear. We have to tell it the end location, X, Y, Z. If you leave one of those variables out, so if you just give it a Y and don't give it an X or a Z, it will only move in the Y direction. If you give it an X and a Y and no Z, it'll only move in the XY, right? It will assume that it's going to stay at the current position for the other values. And you have to give it a feed. How fast do you want it to move? So XYZ feed rate. Again, with the feed rate, you want to use the decimal place. If you do F6, no decimal place, it's going to think you mean 6/10,000ths of an inch per minute. And it's going to take an awful long time to get there, but it'll eventually get there. So the third way the machines move is in an arc. So it can move from where it is to where it is along a constant radius arc. You've got to give it the X, the Y, the Z, the feed, and the radius. And this is G02 for clockwise, G03 for counterclockwise. It's really kind of annoying, but you got the picture, right? So those are the three ways that the CNC machine tool moves. Everything, and there's hundreds of G codes and M codes. Everything else is doing is turning something on, turning something off. Like turn the spindle on, turn the spindle off. Turn the coolant on, turn the coolant off. Or do a peck drilling operation. So peck drilling is when the drill goes in the hole a little bit, comes out to clear the chips, goes back in the hole a little bit further, comes out to clear the chips, goes back in the hole a little bit further, comes out. So there's a macro command or a can cycle command that tells it, do a peck drilling operation to this depth with these different incremental depths, right? So you can do that with one line of code, and then you can give it a bunch of X, Y, Z coordinates after that, and it will go to those X, Y, Z coordinates and drill that same hole again. So there's some things that you can do to speed up the operation. And so when you're doing your Esprit or your CAM software, whatever you're using, and it says, do you want to use a can cycle? There's usually a checkbox. So can cycle means, do you want us to program line by line each of those packs, or do you want us to use the machine tool manufacturer's automated cycle for doing those packs? And it's going to depend. So this G code and NC code, there is no standard. Each manufacturer can implement their own code. Most of them are very similar to each other, but there is no standard. I downloaded the post processor is sort of this software that translates from what the CAM software knows to what the machine tool knows. The post processor is usually created by the people that make the CAM software. Sometimes it's created by some independent people. So I once downloaded a post processor that said that it was created for my Haas lathe. And it was really nice that the Haas lathe had 30 horsepower because we made 4 parts before we figured out what the problem was. And the problem was that we were not making chips. We did all that, like the diagrams and stuff about how chips form. We were not making chips. We were forming the material. We were pushing the material out of the way with our 30 horsepower lathe because the code that it gave us to start the spindle had it start spinning the spindle in the other direction. So we were just mushing metal around. It was a small part. Steel, though. Mushing the metal. The parts did not look good. That's why we kept iterating to try to figure out what the problem was. Turns out the spindle was spinning the wrong direction. Okay, so I hope that helps a little bit. So don't freak out. I think next week, at the end of the week, we're probably starting the lab practicals. Please don't freak out about the lab exam. It is not intended to be hard. And if you do happen to fail it, we actually require you to do it again. Well, you can by failing to show up for your retake that we told you to do. If you try hard enough, you could get lower than an 85. So it doesn't violate laws of physics. And anybody that missed yesterday, I'm sorry, I forgot to click record, but just watch any of the old versions of that lecture.